Let's look at this one. Did you all get the same answer I did? It is negative. It is negative. It is negative. Negative 3,260 kilojoules, or negative 3,260,000 joules. When you look at this, we look at the two half reactions, and the first thing you identify is that we have 3 electrons in one half and 5 electrons in the other. To get them the same, we have to multiply and get 15 electrons. So we look up the cell potentials, negative 0.74 and a positive 1.51 volts. This will be the oxidation half. So it's reduction minus oxidation. We get 2.25 volts. Delta G0 is minus NFE0. And we plug our numbers in, and we get negative 3,260 kilojoules. So those are fairly straightforward once you know the equation. So there are a lot of equations to remember in this chapter. And again, I always suggest that you go back and just write them on a sheet of paper in the front and keep them all in one place, or write them on an index card, whatever works for you. So if we want to stay in the fancy zone, we've already taken fancy to link up free energy and equilibrium constants. We remember that delta G0 is minus RT ln of K sub C, and we just identified that delta G0 is minus NFE0. So therefore, minus RT ln of K sub C is equal to minus NFE0. So we can now relate the equilibrium constant to the cell potential. So now if we rearrange this, we know that minus RT ln of K sub C divided by negative NF is equal to the standard cell potential E0. So if we think about this, and we're talking about E0, yeah, they do. We're not there yet. Okay. If we think about E0, what does that 0 mean? Standard conditions, right? So this little 0 tells us that the temperature is 298 Kelvin, and we know the gas constant R is a constant. So that is 8.314 joules per mole Kelvin. We use that value of R in these calculations because we want our answer in joules or kilojoules. And we know that N is equal to the number of moles of electrons. So when we think about this, R is a constant. The temperature is constant at 298 Kelvin because we're under standard conditions. And the Faraday is a constant. So if we think of R, T, and F all being a constant, and we go ahead and combine these terms and then substitute switching log, the natural log, into the base 10 log. Now, why do we do this? We do this switching logs because chemistry is a really old science. And the old guys who invented this didn't have a calculator. And we know that we have that value of 2.303 that converts natural log into log. And that's how we used to do it in the old days. So it was just commonly done to get rid of a natural log and use a base 10 log because it was easier to deal with, okay, because it came right off the charts. So if we substitute all this in, we end up with this, that E0 for the cell under those standard conditions is equal to 0.0592 volts divided by N times the base 10 log of K sub C. And this is the relationship that we're going to use to do these calculations in this next section. Okay, so now we can relate the equilibrium constant K sub C to the standard cell potential. So let's look at an example of that. Calculate K sub C for this reaction that has a standard cell potential of 0.320 volts at 25 degrees Celsius. Well, if we look at this, we have to first figure out how many moles of electrons there are. And again, I can look at this and say, well, I have the chlorine half reaction is easy to pull out. 2 chlorides yields chlorine plus 2 electrons. So N is equal to 2 moles of electrons. We have to identify the moles of electrons from the balanced equation. So I know that E0 for my cell is equal to 0.0592 volts divided by N times the log of K sub C. So now we can plug in the numbers. E0 is 0.320 volts is equal to 0.0592 volts divided by 2 moles of electrons times the log of K sub C. Well, I have numbers here, so I can go ahead, do the division, and I get 0.0296. So 0.320 volts divided by 0.0296 is equal to the log of K sub C. And when we do the math, that's equal to 10.8. We don't want the log of K sub C, we want K sub C. So K sub C is equal to 10 to the 10.8. Now, when we look at this, yeah, it's going to be a really big number, right? But we would expect it to be a big number if it's a spontaneous reaction. If it goes zooming forward, you'd expect K to be a large number because you have lots of product. And since the delta G is negative and the standard cell potential is positive, you expect lots of product. If you didn't, why would we have a battery if it didn't make energy, right? So K sub C is 10 to the 10.8. Now let's think about sig figs. We are exponentiating or taking the anti-log. So we look at the number of digits to the right of the decimal in the logarithm, and that's the number of sig figs we report. So we only get 1, and we get 6 times 10 to the 10th. Okay, look at the K value. Does it go to completion? Yes. Kc is huge, 10 to the 6th. So it is a product-favored reaction, which we already knew, because it was spontaneous as designated by the standard cell potential and by what delta G would be. Okay, so now you go ahead and do this one. Go ahead and do that with your groups on your whiteboards.